Welcome, everyone. Good morning. This is our fifth and last doctoral meeting session within the program of Aerospace Science, PhD program on Aerospace Science and Technology. Today, we're going to be listening to six presentations, six ongoing PhDs on topics. It's a bit of miscellaneous, but topics related to mainly air navigation and control. We have three talks on optimal control, optimization algorithms for aircraft trajectories. Then we'll see a talk on airborne wind energy related to aeroelasticity by Ivan and so on and so forth. And then space systems, GNC and space systems by Alberto and Alison. So welcome everyone. Thank you very much to the speakers, presenters. Thank you also to the supervisors and the rest of the audience. Hopefully some more people will be joining.
Good morning. My name is Andrés, and during this presentation, I'll summarize the last 3 years of my research. My thesis is entitled Aircraft Trajectory Planning, Considering Ensemble Forecasting of Thunderstorms, and it's supervised by Manuel Soler, Manu Sanjurjo, and Marian Kangarpur. I've divided the presentation in these 4 parts. I will start with an introduction and motivation of my works, following with the different objectives. Then I will cover a couple of methodologies I've been working on. And finally, I will conclude with my achievements and next steps during these years. So let's start with the introduction. I usually like to start my presentation with this slide. This was a Boeing 737, which was flying from Geneva to London Luton. And during takeoff, it went through a hailstorm and ended like this. So it was able to land, but it didn't fly again. And mainly, this is my point, that the storms are dangerous and we must avoid them. Storms are uncertain and dynamic phenomena that account for a lot of delays and disruption in the air traffic management system. In Europe, for example, weather issues causes around a quarter of the delays in 2019. And the objective of this thesis is the design of algorithms for path planning of aircraft around thunderstorms. They must be fast and work in near real time. They must incorporate accurate aircraft dynamic models. And also, we want to make them compatible with ensemble forecast for weather. And I will explain a little bit more about this in the next slide. With these requirements, the idea would be to design a tool that can be included in a flight bag or tablet in the cockpit to help pilots decide their best way around thunderstorms, apart from using another tools such as the onboard weather radar and visual reference that are more limited. Now, this is the main problem. We want to solve a classical optimal control problem, but incorporating uncertainties. We would have a cost function that can include risk, time, or fuel, for example, and we want to minimize it subject to some dynamics, some initial conditions, and some constraints. This problem has been tackled with multiple approaches. We have classical techniques from optimal control, such as nonlinear programming, indirect optimal control, and dynamic programming. But I tested all of them, but I'm using heuristic methodologies. For example, nonlinear programming depends a lot on the initial guess that we choose. Indirect optimal control had a tricky formulation. Any slight changes in the problem can lead to huge changes in the final equations that we must solve. And dynamic programming, I found it too slow for our purposes. For example, once I did a simulation of 2 days for a flight of less than an hour, so that's not good. And moreover, these methodologies have been used typically with deterministic models of weather or probability maps, but in the near future, weather is expected to come as ensemble forecast, including multiple realizations of the atmosphere for each time. So we want to make our algorithms directly compatible with ensembles. And we have explored 2 methodologies, rapidly spreading random trees and the deformation of a graph using the augmented random search algorithm. So now let's start with the first method, which are RRTs. They are considered sampling-based algorithms, as they grow a tree by taking random samples in the search space and connect them to a tree. Our approach was enhanced using GPU, and computational times were reduced a lot, from days to less than a minute. And the idea is to ensure the safety of the final trajectory up to a user-defined safety margin. Now, if you are interested in this method, here I included all our publications, a journal that is online now, and a couple of conference papers with preliminary results. In these three figures, I show how the methodology works. It's an iterative process and during the first iterations, the samples are usually connected to the nearest node. Here, as you can see, the node that is closer in the tree. But as the iteration increase and the density, and there are more samples, there are some routines that connect the nodes to the one that involves less cost to the origin. Here it's a parent, and it connects to it instead of the nearest one because it would involve a higher cost. And additionally, in the last figure, I show some rewiring function that it's continuously rearranging the existing connections in the tree. For example, A30 in the beginning was connected to this node, which was the closest one in that iteration, but after some iterations, that connection changed and is connected to another one. And now some results that were included in the journal paper. We developed a couple of versions of the algorithm, the RT star and the informer RT star. Both are able to run in the same time, around 10 seconds or less, and work with ensemble forecast. However, they are now limited to simple aircraft models and 2D planning. They could be extended to 3D and more complex model, but the simulations would take higher times. And looking at the results, we have the RT star on the left. It's not an efficient algorithm because it's wasting a lot of effort. If the origin is here, it's trying to minimize the cost towards all the samples, but we are only interested in one trajectory. So it's not efficient. If we repeat the simulations and we haven't simulated for enough iterations, it tends to produce different local solutions and get stuck in them. If we simulate for more iterations, it would converge, but it would take longer. It can be the inefficiency can be solved using the informed version. It starts as the previous algorithm, but when it finds a solution, it narrows the search to an ellipsoid and only samples inside it, and this enhances convergence. In the bottom plot, I show how cost evolves with the iterations for both algorithms, and as you can see, the informed version converge way earlier. Typically, in 300 to 500 iterations, it has converged, while the other one takes 2,000 and sometimes 5,000 iterations, which is a lot of time. Now, the second method, which is based on the deformation of a graph. And the intention is to address the weaknesses that the RT presented. So we want an algorithm, again, that use realistic aircraft dynamics, realistic weather forecasts in the form of ensembles, and that it's also fast. And this is running, again, in less than 10 seconds. So first, how to create the graph? We take the forecast at the initial time. We do some clustering of the data. We calculate the centroids, which are the red dots. And based on these points, we define the Voronoi diagram. Then we connect the origin and destination of the trajectory to the diagram, which are these crosses here and here. And then we enclose the whole problem with some envelope. And these little blue dots that you can see along the graph are able to move and will allow the deformation of the graph. So we apply some offsets, and this graph will be deformed. And this is done by the augmented random search algorithm. The graph will adapt to future weather changes and also will reduce a cost function that we will define. This is the problem we want to solve, given a trajectory t and a cost function for that trajectory, j of t. We want to minimize the time of flight and the time that the aircraft spends in. Well, our objective would be to minimize the expected cost given a population of trajectories that are defined in the graph. Each trajectory is defined by a vector of parameters that defines everything. In theta, we include the sequence of nodes of each trajectory. We define the offsets of each of the nodes. We define the sequence of velocities, flight level, everything. And here you can see an evolution of this population of trajectories. The process is iterative. At first, the population covers almost the whole graph, but as we iterate, trajectories tends to collapse to 3, 2, and then 1 solution, as you can see here. And now some results. Here I show 2 cases. On the vertical axis, changing origin and destination, and on the horizontal dimension, I change the weights in the cost function. So if we move to the right, we are just minimizing time, and the aircraft tends to fly in a straight line and don't care about storms. But if we move to the left, we are more conservative and avoid storms. In the middle is just an intermediate situation. So we are avoiding storms, but it might be too risky. For example, we are going through a corridor between storm cells, but it's really narrow and a pilot wouldn't fly through them. And now, to conclude, some achievements and future work for the next year. All the RT research is included in a journal paper that is online from today. Additionally, all the preliminary results were presented in a couple of conferences in Tokyo in 2019 and in the Cesar Innovation Days last year. And also the paper from Tokyo was reviewed and published in a Springer book. All this research about RTs started during my research stay in Zurich in the ETH a couple of years ago. Then I've presented my research in multiple summer schools, usually from Engage, another at a volcanic center in Italy. And also I got a diploma from Eurocontrol, from the Air Traffic Controller Center that is in Luxembourg in 2019 too. And as next steps, I'm preparing a new journal paper with this new methodology about graph deformation. There are many threads open, many things that I would like to test. Also, I would like to test the solutions provided by the algorithm in a simulator and probably present them in a conference. And then I'm planning a second research stay in Switzerland again, in Lausanne, for final of this year or next year. And also, I should be writing my thesis soon. And that's all. Thank you for your attention, and I'm glad to answer any questions you may have.